Reading systems question from process synchronization. We have been given a computer system which is having multiple shared resource types, and there is only one instance per resource type, which means we have different types of resources R1, R2, R3, but there is only one instance of every resource available. And every instance can be owned by exactly one process at a time. So there is no sharing of instances. Owning and freeing of resources is done by holding a global lock. So we already know about the shared locks, exclusive locks, all those which exist over here. And then we have the semaphore things which helps for process synchronization. The following scheme has been given over here in the form of this function, which is the synchronization mechanism being used. So that is customary built mechanism they are using. Let us have a look at what it is doing. There is a function OWNRESOURCE, and this is a resource instance R which is passed to it. So what it is saying that if any process wants to acquire a resource, then this is the protocol that it needs to follow. Let us see what is it. First, it will have to acquire a global lock L. So this global lock is similar to that exclusive lock which we are aware of. So first of all, it will acquire a global lock, and then it will check if the resource instance R is available or not. If it is available, then acquire it, use it, and release the lock. So that is how, if the resource is available, then a process can readily use it. But if it is not available, then in the else case, when the resource is not available, which it is requiring, then what should it do? If that resource is owned by another process P. Now, there is only one instance of every resource, and if it is not available for the current process, it means that it would definitely be owned by some other process. So let us say the instance which the current process is requiring, that R, it is currently owned by some other process P. Then what will this current process do? It will terminate P, which means it will kill that process which is holding the resource that it wants. So if I want something from you, then I will kill you and then I will acquire that from you. So that is the thing going on over here. So it will terminate that process P. It will release all the resources which were being held by that process P. And after that, when all those resources are freed up, then it is free to acquire that R. So it will do so. It will terminate that process, kill that process, then acquire the required resources, use them, and after that it will also restart the process which it had killed. So now this process P will again need to start from the beginning. It will also once again need to acquire all the resources that it needs. So it will proceed on its own. But for the current process which is executing this particular function, what will it do? It is simply terminating it, acquiring its resources. It is restarting that killed process and then releasing its own lock. So this is the mechanism being used. So as we can see, there are some problems in this mechanism, that in this the processes have no priorities. Any process can kill any other process and acquire the resources. So let us check out what are the possible outcomes for this. But before that, let us also understand the difference between deadlock and a live lock. Then only we'll be able to analyze which of them is existing in this scenario. As we know, in deadlock, what happens is there is a loop kind of thing. There are 4 necessary and essential conditions that we are aware of, that there is circular wait and all those things. Mutual exclusion has to be there. But what primarily leads to this deadlock is that the processes wait for each other in an infinite loop. There is no moving ahead. All are stuck. No one can exit out of that loop. There is no progress. So that is what we call as a deadlock. But live lock is a little bit different from that. Starvation exists in both of them. But the difference between deadlock and live lock is that in live lock, you can take an analogy of, it's like a traffic jam, that you are continuously checking if the situation has resolved or not, and the processes are still waiting. There is no progress, but it is not like an infinite loop. They are not dependent on each other like this, which was existing there in the deadlock. There is still no progress in this. there is starvation, but it is like you are continuously banging on the door, you are checking if the resource is free, and as soon as it gets free, you are going to acquire that. So it is not like the processes are dependent on each other, they are just simply waiting for their turn. They are continuously checking if their required resource is free or not, and there is some movement. Here there was no movement at all, absolutely no movement, but here we have some movement, but there is no progress, there is starvation. So we can say that there is no useful work being done over here. Some work is being done, there is some movement, but that work is not useful. So that is what we call as a live lock. So now coming to this given scenario, which of these will exist? Now first of all, check if there is mutual exclusion there or not. As we just saw, at a time only one process can acquire a resource instance, and if the instance which I need, if it is free, then I will acquire it. I will not share it with anyone else. But if it is not free, then I will kill the process that is currently holding it and I will snatch it from that. So at a time only one process is executing, only one process is acquiring a resource. Hence there is mutual exclusion, and there is no violence of mutual exclusion in the synchronization mechanism. So this states that our option D is incorrect. There is no violation of mutual exclusion property in this scheme. So now if there is mutual exclusion, then there can be a deadlock. But do we have a deadlock over here? Let us see. Is it possible over here that all the processes will wait for each other in an infinite loop? No, it is not possible, because every process can kill every other process. So I'm not bound to wait for someone. I will simply go and kill that process and I will acquire the resource which I need. But it is possible that in the meantime I might get killed by someone else. So let us take an example. There are three processes, A, B and C. A needs a resource that has been acquired by B. So what will A do? A will go and kill B, and then A will start executing. But at the same time, what does C do? C also wants a resource that is being currently held by A. So C will go and kill A and it will start to execute. But here, as we saw, it is the terminated process also gets restarted. So these A and B will be restarted. So now they are free to go and kill C and acquire the resource back from them. So this will keep on happening. They will keep on killing each other and acquiring resources. So there is some useless work being done over here. So this is what we will call as a live lock instead of a deadlock, because they are not infinitely stuck. They are free to kill each other and try to execute, which they will possibly not be able to do. So in this scenario, there is a live lock, not a deadlock. So this scheme ensures that deadlock will not occur. And we also know one more thing, that deadlock and live lock, they are mutually exclusive, which means both of them cannot exist at the same time. You will have either a deadlock or a live lock or none. It is not possible to have both of them simultaneously. Hence, if we are having live lock here, deadlock cannot be there. So the scheme is deadlock free. Then the third option, the scheme may lead to starvation. Yes, starvation is there in both deadlock as well as a live lock. Why does starvation occur in live lock as well? Because work is being done but it is not useful. So processes are starving for the resources. Hence there is starvation as well. So we got A, B and C, all three as the correct options. This was an MSQ type question, so we'll be reporting all three.